So it's my distinguished pleasure to announce the last speaker of this conference, Mr. Yongsheng Yao. Please go ahead.
Thank you for your introduction. Thanks for the organizer. This is a joint work with my supervisor, Freddie. It's the brief outline of this talk. I first introduce the background and the motivation of our work. Then I will turn to our main result, the strong Converse exponent for Entanglement-Assisted classical communication. Finally, I conclude this talk with some summaries and open questions. To study the optimal rate of transmission of classical information over the noisy classical channel is one of the most fundamental problems in modern communication theory. The famous Shannon-Sutton theorem has given the formula for the optimal rate, that is the channel capacity. Likewise, Hilbert proved that when the transmission rate is larger than the channel capacity, the error probability goes to 1 divided by it. This property is known as the strong Converse property. So the channel capacity provides a sharp boundary for reliable communication. Although Shannon-Sutton theorem can ensure reliable communication under the assumption that unlimited classical channels are available, in realistic setting, we have only finite results. So an important problem of both theoretical and practical interest is to treat the finite limit setting. There are usually two ways to deal with this setting. The first one is the second order analysis, also called the small deviation analysis. In this setting, we are concerned of the asymptotic expression up to second order is square root of the set of classical message with a constant constraint for the error. Stress first derived the second order asymptotic for classical communication. Hayashi later used the information spectrum method to give a more precise proof. The second one is the error analysis, including the error exponent and the strong Converse exponent. Both of them belong to the large variation analysis region. For the error exponent, we evaluate the exponential decreasing rate of convergence of optimal error when the transmission rate is fixed and less than the channel capacity. Funnel and Gallagher used the random pudding technique to derive a lower bound for the error exponent. Shannon, Gallagher, and Gordon derived the spear-packing upper bound, which matches the random pudding lower bound when the transmission rate is larger than the volume. So the exact expression for the error exponent in the higher region has been determined completely. For the strong Converse exponent, we focus on the exponential decreasing rate of the maximal success probability when the transmission rate is larger than the channel capacity. Our motto derived a lower bound for the strong Converse exponent. Duke and Kroner used the method of type to derive an upper bound. Although these two bounds look very different, it turns out that they are equivalent to each other. So we have a well understanding for the strong Converse exponent as well. Now I will turn to the quantum regime. Different from the classical setting, the classical communication over the noisy quantum channel is more complex. Hollow, Schumann, and Westmoreland first derived the formula for classical capacity of general quantum channels. Is given by the regularized hollow information of this quantum channel. Because the hollow information is not additive with respect to quantum channel, this regularized expression cannot be simplified into the single letter form. So it's NP hard to calculate its volume, and it brings many difficulties to the study of classical communication over the noisy printing channel. As a special and important subclass of the noisy printing channel, the classical printing channel is a direct analogy of the classical channel. It's a linear map that assesses every input signal from an input alpha-bit set, a printing state. The classical printing channel has many nice properties. For example, the hollow information is additive with respect to the classical printing channel. The classical complexity for the classical printing channel has a single letter form. Agua, Nagoka, and Winter proved that the classical printing channel coding also satisfies the strong Converse property. The small deviation and the large deviation performances for classical printing channel coding has been well understood. The second order asymptotic under the strong Converse exponent has been completely solved. For the error exponent, Marco Dalai derived the spear packing upper bound in terms of the page running relative entropy. This upper bound is commonly thought as the correct generalization of the classical spear packing upper bound in quantum regime. Horrell derived the random coding lower bound when the output states of this channel are pure. This lower bound is also in terms of the page running relative entropy. However, when the output states are mixed, determining the random coding lower bound is still a very difficult open question. As introduced before, determining the formula of the classical complexity for general printing channels are very complex. However, when a limited entanglement is used to assist the classical communication, this result will be greatly simplified. An entanglement-assisted classical communication protocol consists of an initial entangled state, the encoding local operations, and the decoding measurement. When Alice wants to send a message M, she first applies an encoding local operation to her part of the entangled state, then transmits her part to Bob over the noisy printing channel. Finally, Bob uses a quantum measurement to recover the classical message. The error for sending a message M and the error of this protocol are defined as follows. Bennett, Short, Smalley, and Petria first give the formula for entanglement to assist the classical complexity. It's given by the maximal quantum neutral information that the channel can generate in form of analogy to Shannon's formula for classical complexity. So the entanglement-assisted classical communication is regarded as the most natural quantum generalization of classical channel coding problem. Bennett et al. Proved the quantum reverse Shannon theorem, and this theorem also implies that the entanglement assist the classical capacity satisfies the strong Converse property. The strong Converse exponent for entanglement assisted classical communication is the exponential decreasing rate of the optimal error towards to 1 when the transmission rate is larger than the channel capacity. Different from the classical setting under the classical quantum channel coding problem, there are not any complete characterization for the small deviation and the large deviation performances for entanglement-assisted classical communication until our work. Data, canonical, and wild provide a lower bound for the second order asymptotic. It's a common conjecture that this lower bound is also optimal. However, it's very difficult to prove this conjecture. Qi, Wang, Webb, and Cheng derived a lower bound for the error exponent based on the position-based encoding technique. Gupta and Webb derive a lower bound for the strong Converse exponent in terms of the savage running relative entropy. Our contribution is to prove that the lower bound derived by Gupta and Webb is also optimal. So our work can give a complete characterization for the strong Converse exponent. It's a sketch of our group. We mainly follow the Musoni and the Alvarez work to prove the strong Converse exponent for classical quantum channel coding. We first introduce the log type of log Euclidean running information for quantum channel with respect to a symbol of input quantum states. This quantity is null and does not appear in any previous work. It's similar to the log Euclidean running Augustine information defined for a classical quantum channel and will be important in our little group. Then noticing that for every pure state by Schmidt decomposition, it can be expressed in this form. By merging the terms with the same coefficient px into a group, we can rewrite it as in this form. These cited are the maximally entangled state on different mutually orthogonal subspaces. That for a symbol consists of this cited and arbitrary probability distribution Q. We can construct Arimoto type quantity based on the log Euclidean running information for this quantum channel with respect to this symbol. And by the variational expression of the log Euclidean running relative entropy, we can prove that this Arimoto type quantity is equivalent to the corner type quantity. Next, we introduce two quantities F1 and F2 according to the range of this probability. From the variational expression of F, it's obviously that F equals to the minimum of F1 and F2. And our next step is to prove that the strong Converse exponent can be upper bounded by F1 and F2 respectively. Then we will get that F is also an upper bound for the strong Converse exponent. I first introduce the proof of the first case. The strong Converse exponent is less than F1. From the definition of F1, for any delta larger than 0, there exists a set of tau bt such that the following two conditions are satisfied. And from the first condition, we can conclude that there exists a set of signal states and a decoding measurement such that the success probability of this protocol goes to 1 as n tends to infinity. And the encoding operation in this signal state can be chosen as in this form. The proof of this conclusion is similar to the proof of the Tuebingen capacity. And we can construct an entanglement-assisted classical communication protocol based on the above protocol. The initial entangled state is chosen as in this form. The encoding operation is the transpose of the encoding operation appeared in the above protocol. And we keep the decoding measurement environment. The success probability of this protocol can be evaluated as follows. By direct calculation, we can proceed to found the success probability as in this form. Because the first term in the first lab goes to 1 as n tends to infinity, we can directly get an upper bound for the success for the exponential rate of the success probability from this inequality. Finally, by the definition of the strong Converse exponent and F1, we can complete the proof of the first case. The proof for the second case is similar to the first case. So now we can get that the strong Converse exponent is upper bounded by F for any probability distribution Q. We can tether this upper bound by taking the epimean over our probability distribution. Finally, we use the Brown pinching technique to convert this suboptimal exponent into the correct one. Lastly, I will introduce the application of our result to the strong Converse exponent for quantum feedback-assisted classical communication. In around feedback-assisted protocol, Alice and Bob initially share an entangled state. In order to send the message M, Alice first applies a quantum channel with output system A1 and A1 theta. The A1 system will be transmitted to Bob over the noisy quantum channel, while the A1 theta system is kept at Alice side for later use. After this, Bob applies a quantum channel D1 with output system X1 and B1 theta. The X1 system contains the feedback information and will be sent back to Alice. The B1 theta system is kept at the box side for later use. This procedure will be repeated for n times. At the last round, Bob will apply a decoding measurement to recover the classical message. Cooney, Sony, and Weld has provided a lower bound for the strong Converse exponent with quantum feedback. In their paper, they asked whether this lower bound is also optimal. Our work can answer this question because by the definition, we must have the strong Converse exponent with quantum feedback is less than the strong Converse exponent without feedback. So our derived upper bound is also an upper bound for the strong Converse exponent with quantum feedback. And this upper bound matches the above lower bound. So we answer their open question affirmative. Is the summary of this talk. In our work, we derived the strong Converse exponent for entanglement-assisted classical communication. Our main result and the main result in Cooney, Sony, and Weld's paper directly imply the strong Converse exponent for quantum feedback-assisted classical communication. we give operational meaning to the train established running control information, justifying its value definition. Although we have a well understanding for the strong Converse Exponent for Entanglement-Assisted classical communication, we know a little about the error exponent and the second order asymptotic for this task. So I think that determining the scale packing upper bound for Entanglement-Assisted classical communication under the corresponding running coding lower bound, and to verify the lower bound of the second order asymptotic derived by data manifold and the value is also optimal, are very important and interesting open questions in future research. And this will establish a perfect connection between the classical channel coding and the entanglement-assisted classical communication. That's all. Thank you very much.
First of all, thank you for finishing really in time and solving problems. That's wonderful. Are there questions from the audience? Are you going to try to work on these open problems at the next plan?
No.
Okay. Well, then let's thank him again.